Hello and welcome to Lesson 10 in the online Terrestrial Navigation course. Before we get into today's lesson, I'd like to thank everyone for all the positive feedback and support for this channel. Just yesterday I hit the 100 subscriber mark and views and watch time on the channel are steadily climbing. So I just want to thank everyone for the likes and the shares, the subscriptions, and for letting the videos play all the way through even though they're not necessarily designed to watch all the way through. All these things are definitely making a difference as far as the channel standing and video rating in the YouTube search results. Also, you may have noticed I've made a few changes to the worksheet designs and have started a Patreon page. For those of you who may not know what Patreon is, it's simply a way for people to help support the channel and these videos financially. If you feel you're getting something of value here and you would like to say thank you financially, you can click on the link labeled Patreon in the video description and make a small monthly pledge for as little as $5 a month to say thank you for the videos or help support future videos. So for less than the cost of a Netflix subscription, you can help support making more of these videos or just say thank you for the videos already made. You can cancel at any time and there's no obligation to contribute to keep these videos coming. So take a peek at it and maybe throw me a bone. I promise you I will appreciate the pledges as much as you appreciate the videos. Okay, now that that shameless plug for money is out of the way and everybody's gone to Patreon and made their contributions, let's see if we can jump into the lesson and learn something here. Today's lesson is probably one of the easiest lessons in the whole course on estimated time of arrival. It's a little bit different than the time, speed, distance problems that you may have seen taking your 100-ton exam or your six-pack exam. But these are the type problems you'll see on the 500-ton mate and up test. We're departing New York. We're headed to San Francisco. We get miles and speed. There's a couple of delays in the problem. We have 32 hours for bunkering and 14 hours for canal transit at the Panama Canal. Gives us a departure time and wants to know our ETA at San Francisco. So we're going to break this down into 5 main steps here. And if you want to pause the video and jot these down, we're going to convert the departure time to Greenwich Mean Time. We've been doing that since lesson 6, so you should be real familiar with that. Then we're going to calculate the total travel time in hours. Distance divided by speed equals the hours. And then we're going to calculate any additional delays and add it to the travel time. Your additional delays could be things like bunkering, canal transit, layovers, etc. Then we're going to take that and add it to the travel time for a total number of hours, and we're going to convert that number to days, hours, and minutes and add it to the Greenwich Mean Time of departure. That will give us the Greenwich Mean Time of arrival, and we will convert that to the local time at the destination. So let's take a look at the problem and see how we're going to do this. First thing we're going to do is convert that 0600 departure time on 16 May to Greenwich Mean Time. Most of your other problems, they've given us a Latin long, and we convert that DR longitude to Greenwich Mean Time. Sometimes the Coast Guard will throw us a bone and do the math for us, which is the case here. They've just given us the zone description of +4 with no Latin long. Some of the problems, they will give you a latitude and longitude, and you'll have to figure that out, but should be pretty familiar with it by now. So we're just going to take that +4 zone description and add it to our departure time. We'll get a Greenwich Mean Time of departure at 1000 hours on 16 May. And now we'll set that to the side because we'll use it in a few minutes. For now, we're going to calculate the total travel time in hours. We've got 5132 divided by the speed of 13.5 knots. And it's going to give us a travel time of 380.148 hours. And this is just one of the little nuances here that may hang you up, but you'll notice I only put the decimal place out to 3 places here in the video, and that was just for my convenience. We're going to need to leave that whole decimal in the calculator when we work the problem. So we're going to say 5132 divided by 13.5 equals 380.148 blah blah blah, real long decimal number. And it's pretty important that we leave these decimal numbers in the calculator for the next few steps. So now we're going to take the additional delays, the 32 hours for bunkering and the 14 hours for canal transit, and we're going to come up with 46 hours of delay time, and we'll add that to our travel time. And again, here I've just carried the decimal place out 3 places, but when we put it in our calculator, I'm going to add 46 to it, and we'll keep that decimal in our calculator. That gives us the total hours, and we need to convert that from hours to days, hours, and minutes, and add it to the Greenwich Mean Time of Departure. So we'll take that whole thing and we'll come up with 17.756 days. But in our calculator, we're going to divide by 24. And we've got that decimal. And then we're going to subtract that 17 from it, because that's our days. So minus 17 equals, and we'll leave that decimal. We're going to multiply this decimal times 24, and that gives us 18.148 something hours. So times 24 equals, now we're going to knock off the hours and set them over to the side. And this last decimal is going to be our minutes. This is the only one that we're going to round. We're going to knock off the whole number here of 18 minus 18 equals, multiply that decimal times 60, comes out to 8.8, and we'll just go ahead and round that to 9 minutes. So that's going to give us a total of 17 days, 18 hours, and 9 minutes. The only nuance here is just keeping that decimal in the calculator. Knock off the whole number, do the next step, then knock off the whole number, do the next step. It's relatively easy once you get into it. You'll notice it does work out pretty easily. So we'll take these numbers and start adding them to our Greenwich Mean Time of Departure. First, we'll take that 17 days and add it to the 16th of May, and that lands on June the 2nd at 1000 hours. Now we'll add 18 hours to our 1000 hours. That'll put us at 04 on the 3rd of June. Now we need to add the 9 minutes to it. 0409 on 3 June is going to be our Greenwich Mean Time of arrival. And now we need to convert that to local time at San Francisco. Now, up until now, we've always converted local time to Greenwich Mean Time, where you add west longitude and subtract east longitude. Here, when we are converting from Greenwich back to local, we do just the opposite. So if our zone description at San Francisco is +7, to go from Greenwich to local, we will subtract that 7 to get local time. And it gives us a time of 2109 on 2 June as our local time of arrival. All right, well, some of these problems, they do not have any delays in them at all. At that point, then you're just going to take your travel time and convert it to days, hours, and minutes, add it to your Greenwich Mean Time of departure, then convert that to local time, and everything should work out. All right, if you like the videos, just give them a like and a share, subscribe to the channel, and I'll get to work on the next one. Thank you.